Thank you very much for inviting me to give this talk, and welcome to King's College London. So after the talk, there will be a little demo. So those of you who would like to hear the demo, please stay and we'll take you to our audio lab. And so we'll be presenting the demo, who is one of the co-authors, my former PhD student here. So what I'm going to talk about is perceptual sound field reconstruction, recording and synthesis. This is, as I pointed out, joint work with Enzo De Sena, who is here now, and Hussein Haji Habiboglu. Hussein now is professor or associate professor at Middle Eastern Technical University, and Enzo has Marie Curie Fellowship, and he's now in Catholic University of Leuven. Oh, is this? I disconnected it. Works better when you turn it on. So I'd like to point out that I'm really terribly indebted to James D. Johnston, better known as JJ, for introducing me to this research. Then James Hall, who was my student here, master student, for preliminary work which led to this grant that we got from EPSRC. Francis Ramsey for providing his support and collaboration in early stages of this project. And Julius Smith, who we are collaborating with now on artificial reverberation that relies on techniques that we developed. And of course, EPSRC for providing the funding, and our Faculty of Natural Mathematical Sciences for providing additional funding for some extra equipment. Okay, so the overarching goal of this project, and we're going to talk about, are actually low-count multi-channel systems, up to 10 channels, which are capable of transposing us to actual venue of recording of a music or acoustic event, or actually creating a very convincing illusion of presence in some virtual space that does not exist, like for gaming applications, etc. So towards that goal, specific objectives that we want to achieve is to first understand principles involved really in depth, and based on those principles design systematic and scalable framework for building such systems, and ultimately to provide some practical solutions. The experience of spatial sound can be achieved in many different ways. At one end of the spectrum, we have binaural techniques, which rely critically on psychoacoustics to generate ear signals, which are then presented mostly via headphones for the audience of one. Presentations can also be done over loudspeakers with cross-channel cancellation, etc., crosstalk cancellation, but then we have all these problems. The stereo sound is being compromised by head movements, etc. On the other side of the spectrum, we have wavefield synthesis techniques, which are actually not relying at all on psychoacoustics, but employ a huge number of channels to create physically accurate approximation of the sound field that we want to generate. And of course, while they're employing all this equipment, they can create actually a large sweet spot, which is convenient. It can work for large audiences. And because we have all this kind of high level of equipment, we do not really need any kind of psychoacoustics, so it is all sort of physical. In between are these low channel count systems, which is commercially viable equipment, something that we have at home, like 5 to 10 channels, which then aim or should be capable of providing some sort of sweet spot for a small audience of like 2-3 people, in such a way that that sweet spot is stable, so we can move a little bit around the room and still have that stereo experience. Since we do not really have too many channels to create a very good physical approximation of the sound field, we must rely, in order to achieve that, we must rely to a large degree on psychoacoustics, and that's where actually the main problem is, which we want to answer is what is that about psychoacoustics and how to take advantage of it to achieve this goal. Unfortunately, currently available low channel count systems are actually yet to achieve the spatial realism, which is possible with the available number of channels. One of the main reasons for that of them still not performing optimally is that current multi-channel surround sound systems are actually still based on the legacy of sound production for film industry. The which we had for many decades, the main focus of which was to create some attention-grabbing effects, where we would actually sort of generate some sort of auditory perspective by some pairwise panning between speakers in front of the listener and provide some general ambience feel. And very little actually attention is normally being paid to making sure that that auditory perspective is consistent with the acoustics of some realistic space, or consistent or coherent also with reverberation that is being provided from the back speakers. And they're heavily mixed and actually are very complex and rely primarily on the skills and art of Tonmeister. And actually everything is sort of more in the domain of creative industry, although there is actually quite a bit of scope for actually some very, very solid engineering there. Not to say that skills of a Tonmeister are not important, but there is much more that we can do with engineering to actually sort of make the job of Tonmeister much easier than it is so far. So one attempt and notable approach in the direction of introducing some formal approach and scientific approach is ambisonics, which actually tries to do a physical approximation in the center of the listening space. However, it has never really become a commercial success, and maybe the reason is its sophistication, technical sophistication, and also because the sweet spot is not stable, it actually gets compromised very quickly with small movements around the sweet spot. Of course, I mean, if we introduce high level of equipment, then we can do better and better, but what is sort of the optimal way we can achieve with given equipment? That's something that we want to do here. So towards achieving convincing spatial sound, first, there is the main scientific challenge that needs to be overcome is to decide what is that about the sound field that we need to capture, and then which sort of boils down what is going to be the microphone array and how to design that microphone array to acquire all the information that we need from the sound field in order to then enable reproduction of that sound field in a way which is going to sound very convincing and feel as transposed back to the space where we are. Playback scheme, so what we decide here is that actually each of the channels of the microphone array is going to have a dedicated loudspeaker, and we will be reproducing those without any mixing. So this is also relying a little bit on some early work by Fletcher from the 30s, which under certain conditions sort of established then any kind of mixing of the channels. He was using only 3 channels, is blurring the auditory perspective. So we are not really going to deal with details, but say we're going to make the choice. So we are going to have microphone array, and each microphone is going to have dedicated loudspeaker and just produce whatever we record there. So One solution, the first solution in this direction was provided by Johnston, and which he referred to as perceptual sound field reconstruction in 2000, using a 5-channel system, and that is what actually was our starting point and inspiration for our work. So what Johnston did, he used a 5-channel system. And he used a regular circular microphone array and loudspeakers in the same configuration. What was the motivation behind this choice of 5 channels? Again, he was also relying on another work by Fletcher, which established that 3 channels seem to be minimum for providing convincing auditory perspective in the horizontal plane in front of the listener, and the reasoning was then perhaps 2 more would be enough to extend that auditory perspective to 260 degrees. And there was also a work by Ando and Kurihara, which established that 5 channels seems to be minimum for rendering properly diffuse sound field. So if you have a limited number of channels, then we can be only so ambitious. And what we are going to try to achieve is to have a very convincing auditory perspective. That means that the listener can say where is the sound source for all possible sources that are involved, and to have a sort of very convincing illusion of a diffuse sound field and or reverberation. It's not that we can really achieve everything there. So, and what was Johnston's array then like? So he said that what was critical is to have this diameter of the ray is 31 centimeters, which is the distance the sound travel from one ear to another ear around human head. So the diameter is actually larger than the diameter of the human head. And in that way, he said, what this design aims to capture is actually intraaural time and level differences that a listener would experience at the performance, at the venue of this acoustic event. And he said that that's going to be achieved if he designed this used microphone array, which has diameter of 31 centimeters. In order to capture intraaural level differences, then Johnston then proposes to use directive microphones, which would have attenuation 3 dB to adjacent microphones and basically infinite attenuation to the second adjacent microphones. I guess I should not be spending in front of this audience time saying that what's actually critical for our perception of source directivity is intraaural time and level differences that a listener would experience. So I just glossed over it and went immediately. So that was Johnston's design, and actually in psychoacoustic experiments and so on, that actually very good results were achieved. Now you might be asking, so well, I mean, this sounds reasonable, but is it really so? And you might have lots of questions now after I presented this, and so we did. And one of the first questions was, is the proposed array radius really optimal? Can we do better? And why is it really that we need to have this radius, which is exactly the distance the sound travel around human head? Are those polar patterns of microphones really optimal, or can we design them to be better and have better system? Then yes, even assuming that we are capturing those original intraaural time and level differences, are we really reproducing them back? Because we are playing back over 5 channels, and all these channels are mixing, so who knows what we really have there. Then how to generalize this to systems with more than 5 channels and to some irregular configurations. And that is where we're starting our research. So we decided to depart from the original idea, because there is no way that we can guarantee that we are going to reproduce exactly intraaural time and level differences that a listener would experience there. But instead, what we are saying, well, we are going to decide, and we are going to produce inter-channel time and level differences, such that when reproduced, the listener is going to have the impression of the source in the correct direction. And we are not going to worry about whether this is really intraaural time and level differences, but these are some time and level differences between channels. And then what I'm going to present here, how we are doing that, so you're going to notice that I'm not going to really restrict any considerations to 5 channels or any kind of regular patterns, except sometimes in experiments. And basically, what this is going to boil down to is what is going to be array diameter that we are going to use. We're still going to stick to circular microphone arrays, and what are going to be microphone polar patterns to achieve this. That is to have a proper auditory perspective of an acoustic event. So now, and as I said, we really need to rely quite a bit on psychoacoustics, and the psychoacoustic knowledge is very fuzzy, and it's described by plenty of curves, and depending on the kind of stimulus, we have a different curve, and it just is a mess. And what we are sort of more comfortable is little bit of mathematical analysis, and we are saying, well, we have 5 channels, we don't have too many channels, and we cannot really hope to achieve something which is going to be very good approximation physical of a sound field in a large area, but at least we should be able to reproduce some very simple sound fields, and based on that we are going to assess our different kinds of design choices on their ability to reproduce some simple sound fields. And what we are focusing on, we are doing now mathematical analysis for monochromatic plane waves to just narrow down the scope of all these parameters that we are going to consider, because one rationale is that many more complex sound fields can be actually represented as a superposition of monochromatic plane waves. So if you find something which is going to give do badly, or even in this kind of case, that's not going to do better on more complex. And if it's doing well on monochromatic plane waves, then there is a hope it's going to work well in a more complex case. So what we are doing is, again, we are analyzing this situation. So we have two microphones and a plane wave coming from a direction between those two microphones. And we have also loudspeakers which are in the same configuration, the same angles, but we're having this plane wave assumption. So, and here we are actually, we are just showing here one sector, but we have like an arbitrary number of microphones with arbitrary angle. It's just that they are all on a circle of a given radius. And we are doing our analysis using the notion of active intensity, which is the product of the pressure field and velocity field, which is complex for monochromatic plane waves, and its real part is the so-called active intensity field. So what's known is that the direction of this active intensity field actually coincides with the direction of wave propagation. So one thing that we want to answer now by doing this active intensity analysis is the following. So when we are doing this reproduction of a given direction of the sound field, whether for each given direction we should actually involve only two adjacent channels, or we should involve all channels that we have, which is not something which is obvious answer, because one may think that if we involve for every direction more channels, there is more that we can do. And it turns out actually, and something that our analysis shows actually, that it is optimal that for every direction of sound wave propagation, we just employ those two channels which are adjacent to that direction and minimize the effect of all other channels as much as possible. And that is something that also agrees with some psychoacoustic experiments in a paper by Lee and Ramsey. So that is going to be one restriction that we are going to introduce. And here is illustration of active intensity field. So what we have here is our active intensity field for 500 hertz plane wave. And this is for 1 kilohertz plane wave. What you see here are all these arrows which actually, the direction of arrows corresponds to the direction of wave propagation. Their length corresponds to the intensity of sound field there. And the gray level corresponds to the accuracy, actually, or the error of reproduced direction. The darker it is, the larger the error. If it's white, that means that the error is small. So what we see here in the first row is that what we obtain, if you have 5-channel system, using again the diameter that Johnston proposed with just omnidirectional microphones, we can see that basically there is nothing really, there is no direction or any kind of uniformity. We are trying to reproduce monochromatic plane wave coming from this direction, 45 degrees. So now we are introducing first order cardioid, and we can see that already here we see a little bit of an order. And here we have third order cardioid, which means that we are actually minimizing the effects of neighboring on channels other than two adjacent channels, and we are having better and better picture. And we actually show mathematically that actually it is optimal to use just two channels. This is just for illustration. So another thing that we also wanted to figure out, what is the effect of array radius, whether it should be 15 centimeters or more, and so on. And it turns out that the effect of this array radius is that these stripes just move in direction perpendicular to wave propagation. That means that, well, perhaps the array radius is not really all that crucial, and we are not going to worry about array radius for now, and we are going to do all the analysis for just any kind of array radius. And then also, another thing that we can also evaluate in this way is the effect of number of channels. Of course, the more the merrier. If we have more channels, we can do better. But we are able to do some quantitative characterization of what happens. If you have more channels, then the width of these stripes actually becomes wider. And we can have then, we also have this closed form expression on how exactly the impact of, what is exactly the impact of channel on the width of these stripes. So now we decided each direction will be reproduced by just two adjacent channels. And now what we want to see is how to design those polar patterns in order to achieve that time and level difference captured by those microphones are actually going to be such that when we play them back using loudspeakers, we have impression of the sound wave propagating in the correct direction. So we need to provide time and level differences properly. However, once we decided on how many channels we have and once we decide on the radius of the array, so given direction of the propagation of the sound field, the time of arrival between these two channels is completely determined by this geometry, and we are not really having any kind of control over it, and there is simply geometrical kind of relationship, and that is going to be our interchannel time difference for a given direction of the sound. Now, what we want to do and what we need to do is to pair that interchannel time difference with interchannel level difference, so that when they're combined and reproduced, we have perception of the sound field, of the sound wave coming from the desired direction. And we are going to achieve that by designing properly polar patterns, because we have already given time differences. And in order to design polar patterns, we're using well-known psychoacoustic curves. And here what these curves are. So on the horizontal axis, we have time differences between channels in stereophonic reproduction. Imagine two loudspeakers in front of the listener, and they have different time and level differences. So here we have on the horizontal axis time differences. Here we have level differences. The left curve, this curve represents all pairs of time and level differences which are going to create perception of the sound wave coming from the direction of the left speaker. And these pairs are going to create perception of the sound field coming from the direction of the right loudspeaker. And everywhere in between the sound, we are going to have perception of the sound coming somewhere in between the two. Now, once we decide on what is going to be our, radius of the array, and angle between microphones, basically we have immediately the maximum interchannel time difference, which is going to happen when the sound is coming from the direction of the left loudspeaker, and that is actually setting this operating point here. And this is going to be the negative of that, or the opposite of that, when the sound wave is coming from the direction of the right loudspeaker. So basically for sounds coming from directions in between, then we are going to have time and level differences operating somewhere on this curve. Now, what we are going to do now is that we are going to design our polar patterns in such a way that as the sound is moving from one direction to from direction of one speaker to the direction of the other speaker, then we have all these level differences described given by one of these curves, lines, that is connecting these two extreme points. It is unclear what is going to be the right or the best curve. So initially what we were doing, we were just taking the straight line. Turns out that implementing straight line would actually require higher order microphones than what is practical. Then we actually tried something with second order polar patterns, and that is what we obtained. Turns out that in acoustic experiments, actually, this gave also better results than just a straight line. So that is still optimal question, which exactly line to take, but it doesn't seem to be making too much difference as long as we're having some monotonic line going from one endpoint to another. So, and using that, so here we have some sort of closed form expressions for this. I'm not going to go into details, but that's described in our papers. So here we are showing some examples. So we are showing comparisons of polar patterns, for instance, for second-order ambisonics with mode matching, which is green line, second-order ambisonics with in-phase decoding. Then we are showing the curve, which would be obtained with 5 channels for tangent panning law, which means just intensity stereophony. So these are all these different curves, and we can see that actually this tangent panning law intensity stereophony actually requires very, very selective curves. Here we show examples of what we obtain using time intensity. Now we have time and intensity. And what is our approach? Here we have first Johnston's curve, which here we see like 3 dB attenuation at the neighboring channels. And we see actually that what we obtained by doing careful considerations and following known psychoacoustic curves, those which I presented are due to Franzen, but there are other curves which were done for this purpose. We see that actually we would need something which is going to be more selective than initially suggested by Johnston. So, and we are doing now psychoacoustic experiment. So we place a listener here somewhere in the center of the room, and we are playing back sounds using two loudspeakers, and then we were also looking in these areas around and so on. And we have a number of pointers, and we are just asking, so where do you think the sound is coming from, and so on. And that is what we measured. I'm not going to go through details of this one, but so now if you're in the center, for listener in the center, basically all these techniques perform sort of comparably. This is higher order second order ambisonics with mode matching decoding, except that higher order second order ambisonics with in-phase decoding is not really performing all that well. But now, when we look at what happens when the listener is a little bit off the center, we can see that that the time intensity techniques is actually performing as good as the better of the ambisonics decoding techniques. Not necessarily completely everywhere as good as tangent bending law, intensity stereophony, but I'm going to according to this criterion, but there are other criteria. But you should notice that actually this intensity stereophony, if you are to record, that would require very, very high order microphones. So that is not something that we can really implement in recording properly. So now another criterion that we use to evaluate these techniques is the so-called locatedness, which is the how convincing or how certain a listener is about the position of the sound source. Well, say, well, you know, I think it's somewhere there, or I'm sure it's there, etc., etc. And we conducted those tests. So we can see again that when the listener is in the center, they all techniques work well. So this is time intensity, this is high order ambisonics, second order because it's 5 channels, etc. In phase and intensity stereophony. And we have two reference point, which is completely diffuse anchor, and something which is like the best, completely precise, etc. So they all perform well when the listener is in the center, but when the listener moves off the center, we can see that ambisonics degrades. Now, actually, mode matching degrades faster than in-phase decoding. But what actually then got surprising is that actually this time intensity stereophony turns out to be more stable than intensity stereophony, and that is something which is kind of a new insight into this whole field. Because most people would believe and argue strongly that intensity stereophony is crisper and it is more stable, etc., etc., which probably is the case. And there are papers written on it, but nobody was evaluating time intensity with time and intensity cues being provided properly, which is what we discovered here. And we show that if you do that properly, then we actually have better stability and locatedness than intensity stereophony. Okay, so to conclude this part of the talk, there is more coming. Is that we basically showed here that given an arbitrary array radius, we can always design those polar patterns in such a way that we can have a good auditory perspective. That means that the listener can tell, and stability of the sweet spot. It's not that one can walk like 2 meters away from the sweet spot, but still we are doing better starting from scratch than competing methodologies. But we see that that leaves array radius as a free parameter, which leaves some further freedom to optimize some other parameters. And this other parameter that we are going to because we haven't really given any answer to what is the optimal array radius yet. And one parameter that we are going to try to optimize is so-called naturalness or locatedness. It turns out that there is a not so clear distinction between that locatedness and naturally sounding sound, and now I'm going to explain why that is the case. So when we are reproducing, when the listener experiences, when there is a sound source somewhere in the space, and we listen to it, so that sound source wave field would actually create certain time and level differences in critical bands of human hearing. And actually, given source in a given direction, so all this time and level time we have on the horizontal axis, time differences on vertical axis level differences, and we have certain pairs in it, and each one of these plots corresponds to one critical band of human hearing. So in each of the bands, sort of these time and level differences are going to appear in these pairs, which are described by these curves. So not only that they're going to be, these pairs are going to be on these particular curves, but they're also going to be consistent as to across different critical bands. Now, if we happen to have stereophony, that is, we do not really have one source, but we have two loudspeakers trying to create impression of a sound in a different direction, which is something else somewhere in between, then we are going to have pairs of time and level differences which are not going to be on these curves, and they're not necessarily going to be consistent with each other and coherent across different channels. So now what we are doing, so that's why we say that naturalness, that to achieve better naturalness, what we are going to try to achieve and see how array radius would matter in terms of getting something which is as close to possible to what would happen with the just original sound source rather than stereophony. But now comes another question, is like, how do we measure this distance or agreement with something which is natural, with something which is produced by two loudspeakers? First, we need to measure some sort of a distance in each of the individual bands, and then we also need to aggregate those distances somehow in accuracy across different bands, and then turned out not to be a trivial issue. So one thing that we could do is that, let's say, in one of the critical bands, what we can look at all these pairs which correspond to natural sound sources, and then there would be something which would be produced, pair of time and level differences produced by two loudspeakers producing the sound, pretending it's somewhere in between. Now we can measure now distance from each one of these locations. So and each point here corresponds to a specific location of the real sound source. So what we can measure distance from each one of those points, and that would somehow, if you say, well, whatever is the closest, that would be some sort of the impression based on that channel of where the sound is coming from. It turns out that if you look at the two Euclidean distance, then we are not really getting something which agrees with psychoacoustic experiments. Most often we would obtain that the closest impression we get would be close to the center. It is known, however, that from psychoacoustic experiments that actually, when we have something which is way off natural, then the listeners actually perceive sound sources either here or there, closer to extreme points away from the center. In order to capture that, we are using 0.2 quasi-norm, which is actually this kind of norm. So all points along this figure actually are the same 0.5 distance from the center. So now to see what is happening and what is the perception, or to evaluate the naturalness of the reproduced sound field, we actually calculate these distances using 0.2 norm from all these points in each of the bands, and that is going to give a particular curve in each one of the bands. So basically, now we invert that, and where the peak is, that would be sort of the idea of where the interpretation is of the sound source coming from what direction. Now we know that the auditory system is then aggregating all these across different bands, and what we are doing, we are then averaging all these curves, and then we are looking, calculating the entropy of this average curve, which is going to give us some idea of what is going to be how convincing our impression of how certain we are about the direction of the sound field. So there is much more to it, and there is a reason behind each one of these choices, much more deep than what I'm explaining here. But that's basically the main idea. And now we were comparing that measure of naturalness or locatedness with our locatedness experiments, which I just showed previously, and we're actually having very good matching with our experimental results. Previously, people would actually pay attention either to time differences or level differences, but there hasn't been work which is actually combining both and providing a unified, just one measure of what is locatedness and what is our certainty about the location of the sound. And we presented this at ICASP, and conference paper is in preparation now. So What do we do with this now? We said that we want to figure out what is actually optimal array radius in terms of this naturalness or locatedness. So, and how do we use it? Now again, we are looking at two-channel system, and we are playing different time and level differences between those two channels, and we are showing them here. And then we are using some computational model, time differences and level differences. We are using well-known computational model, I think it was Guy's model, to actually calculate those time and level differences in these critical bands of human hearing. And then we are using the function that we just, our method to evaluate naturalness based on those. And that gives us this figure here. So where we see all these gray levels which correspond to the level of naturalness. If something is dark, that means it's not natural according to our function. If the lighter it is, the more natural it is. Now, what we see on this curve, on this figure, we see this red curve, which corresponds to time and level differences between channels, which would be obtained with 15 centimeters array with 5 channels as considered initially by Jim Johnston. And we can see basically that the curve is operating in a zone which is not really so bad. Of course, in the center we have really completely white, and sort of that's not really problematic to achieve. But we can see also that if we were using just intensity stereophony, just level differences, we would be operating on these curves. On this curve here, where there would be no time differences, and that will give really good results. Now, as soon as we move away from the center, the whole picture is moving like this, and here is where we operate. Well, it's getting worse, but it's not really dramatically bad. On the other hand, tangent panning law or intensity stereophony actually gets affected much more. So based on that, we can say that, well, we can perhaps even look at some larger radii here, because that would make us operate in this region, and if it's a little bit away from the center, then it would not be really as bad. So that is sort of one of the tools which sort of can provide guidance on what would be optimal array radius, or what would be adequate pairs of time and level differences, and also explains mathematically our observation why time and level differences combined actually perform better than just level differences in terms of stability and locatedness. Now, that is all fine. So we found a way to put a microphone array and record it. So, and that was all done with simulations and so on. But we said that we actually need to have very specific polar patterns in order to achieve these time and level differences. And now the question is whether we can achieve them, because microphones that are available in practice are sort of low order microphones. Otherwise, they become very expensive. So, and then we were also looking at some ways to actually produce some high order microphones. In this time intensity stereophony that we use in this time intensity scheme, we were using results which presented were with second order microphones. But if we want to have more channels, that was only with 5 channels. If we want to have more channels, we would need something which is going to be more selective. And then we proposed a novel scheme for actually designing differential microphones, and it turns out we actually managed to design something with very good characteristics over 5 octaves, using third order polar patterns, using only 7 omnidirectional microphones. And I'm just going to show, and we actually, Enzo, I should not say me, Enzo built a prototype and did all the measurements. So this is the prototype that we built, and these are measurements with that prototype showing fantastic characteristics over 5 octaves. So I mean, the only reason why we have this particular kind of polar patterns is something that cannot be achieved with polar patterns which are available with existing structures. So that is something that can be achieved only with this new structure that we proposed, and we showed that actually works really well, and we can make it really cheaply, even prototype, etc. Now, another thing that that is actually here very important is the following. We said so far I was focusing on recording an acoustic performance and then reproducing it, so that we have impression of being there present in the space where it was reproduced. I was just talking about direction of single waves or sources, but basically what is happening with this microphone array, that microphone array would capture directions, direct sound field, and would capture all reflections. So all these reflections would be sort of rendered with accurate directions by means of this microphone array. So in that way, in one go, we take care both of direct sound field and acoustics or individual acoustic sources and also reverberation. Now, on the other hand, now we said that we were looking also into synthesis. The way we do synthesis is we then have we just simulate this microphone array. We have a space which we want to simulate. We put our simulated microphone array, and we capture the signal that microphone array would capture given certain acoustic scene, and we just reproduce those sounds, and that is the way we synthesize an acoustic scene or virtual space. Now that would also work well for spaces which are static, but it's not satisfactory if we want to render some dynamic scenes, because calculating all these impulse responses that we would need to use to convolve our sound sources with different reverberation, etc., that would take forever. So what we are doing is that we propose then one scheme which is actually providing very good perceptual approximation of reverberation, or basically very good perceptual approximation of the whole sound field that would be generated in a given closed space. But we are doing it in such a way that we make sure that we render direct sound field, the line of sight wave correctly, and first order reflections correctly, and then as the order of reflections actually grows, then we are actually making coarser and coarser approximation. And how do we do that? So let us look at an enclosure. So we have a source and we have a microphone here. We said that in order to do this, we are basically for this stereophonic recording or perceptual sound field reconstruction, we would have 5 or 6 microphones, as many as we have channels, but let us focus just on one microphone. So we know that first we have this line of sight direct wavefront that comes to the microphone, but then we have first order reflections, then second order reflections, etc. And one method which is actually working well for getting all these reflections correctly is image source method, but that actually takes quite a bit of time to calculate. So instead of calculating all these images of this source, what we are doing, we are simulating each one of these walls by just one node. And that is going to be exactly the position where the first order reflection is going to hit the wall. Now, we are reflecting. Now from these reflections, from these nodes, what we are doing, instead of finding accurately all higher order reflections, then we are actually looking at each one of these nodes actually reflecting to all other nodes, and that is how energy is circulating. And of course, each node is reflecting also to the microphone, and that turns out to be very, very cheap to implement. And that basically means that we are making coarser and coarser approximations of higher order reflections. Only the line of sight and first order reflections are rendered accurately, and they're actually what's most important for rendering proper auditory perspective. And then everything else is being replaced by approximation. But starting from high order reflections, second order reflections, the listener cannot really hear where that reflection is coming. And what is most important is to have proper reverberation time, to have build up normalized echo density, the way it is building up, and to have proper nodal density, etc. And we are actually doing all this kind of we did all these objective evaluations based on perceptual criteria. One would be reverberation time. So we are comparing to reverberation time that we obtain using our model with two known formula for estimating reverberation time, and we are always in between these two. I'm not showing other results, but we actually, since recently, we actually performed more experiments and to calculate also normalized echo density, which is also known to be highly correlated with our perception of certain auditory space and modal density. What else did we compute then? So basically everything there is for kind of...
For sort of reflection, reverberation,
yeah.
modal density.
Well, anyway, so this basically takes no time to compute, because you can see this is nothing else. The model, the mathematical model for this, the system that we are using is basically not more complex than feedback delay network. So that is just a recursive system. It just, instead of sort of tweaking and guessing what parameters would be, we actually get parameters directly from the space, so that we have completely correct rendering of first-order reflections and direct line of sight, and everything else becomes coarser and coarser approximation. But basically, so that is sort of one kind of perceptual approximation of image source method, which has complexity of feedback delay network. So basically, we are getting the best of both worlds. So basically, that would be all that I had to say. And so what we presented here, what I think is important is, as we are engineers, we want to understand, not just to design something to work well, but we want to know why it works well. And I think that we actually gain lots of understanding on why certain things work well, and what would be the direction, and what is really a framework for designing such a system, stereophonic system, for sort of any arbitrary number of channels. Of course, we are up to getting to something which is wave field synthesis. And it is applicable to, as I said, also to irregular configurations. We did experiments with regular microphone arrays and with 5 channels in order to have comparison with what was proposed initially by James Johnston. But basically everything that we did is applicable to irregular configurations. So now what we're looking to do is to extend this to 3D systems and to extensions to large-scale systems to see how that scales. And sort of when it becomes perceptual, stops being perceptual, becomes really physical, the borderline between wave field synthesis and this low channel count systems. So that is all I had to say. So if you have any questions, I'm happy to answer. And afterwards, if you would like to hear a demo, you would need to wait here, and we'll take you to the lab, and then so we'll be presenting those demos. Some of them are actually quite interesting. So. Yeah.
So you say the array radius really has no effect on the efficacy of the system? Or
Well,
is there a minimum array radius where you lose any form of useful interaural time data? There must be, surely.
Yeah. I should have said it's not that critical.
Right.
That's it. I mean, it's all based on psychoacoustics.
Yeah.
Sort of, and when we speak of psychoacoustics and psychology, we can never say anything for sure, really. But basically, that's why we were plotting this from the physical perspective. I mean, for instance, Johnston thought that 15 centimeters was very, very important. Now, from the physical perspective, now, if you're reconstructing these monochromatic plane waves, this is the effect of the radius. It's just that all this is sort of shifting. So yes, now the sweet spot for one frequency may move a bit, but basically they're all moving across all frequencies. So basically, it's still, we are going to be in good position. It doesn't really matter whether they're all perfectly aligned or not.
Okay, sure.
That is what I'm saying.
What was
that is from the physical perspective.
Yeah.
From our psychoacoustic experiments, and also one should also note that basically much more complex sound fields can be represented as a superposition of those. So basically, that and we can have quantitative characterization of how much this moves and so on. So that is the effect of array radius. Now, if you look at experiments, we were looking also at pushing it all the way down to zero radius. And we were implementing also tangent panning law. But I would also like to point out that tangent panning law is different from what would be obtained had we followed these curves here. So, and we were doing experiments with that too. And as you can see that basically, well, you can see that if you actually push it to very minimal, then we are losing. This red curve corresponds to basically it's very close to zero, right. Zero radius. So yes, at some point we are going to hit. We are now comparing 15 centimeters to 0. Right. Centimeters, and of course, if you make it large, at some point is going to break. Where it's going to break, we don't know yet. People were looking, and there were papers written about all these problems with time intensity stereophony, and they're really known problems. But all that work actually pertains to really large arrays, like 2 meters or something like that. So yes, where is that point where it breaks, we do not really know yet. But here is also these curves here can provide some guidance. So as long as we operate somewhere here, then we are fine. Of course, if you go something like that, which would be a very large microphone array, then it's not good. But we do not have definite answer. But definitely, it's not the array. The radius is not really that critical.
And practically, how did you, I mean, if I understood you correctly, you were trying to only have 2 mics picking up any given sound source at any time and coming from 2 speakers. You didn't have 3 speakers going. How did you, what level of attenuation works between, because if you've got an array of N microphones, what level of attenuation between any pair of microphones invalidates the model?
Yeah. So our model is what we. Okay, so if you have this, so this is like center of this one. So basically, the reactivity should be such that by the time we get to here, basically this should have. This microphone should have minimal contribution. So whatever is perceptually acceptable, that could be minus 15 dB.
So you found 15 dB was reasonable? Yeah, 15 dB
was reasonable, and I think that is what we achieved. There are some psychoacoustic experiments basically saying that whatever this one picks up coming from this direction should be negligible, should not be heard.
So 15 dBs
compared to this.
15 dBs is considered negligible, or above that is negligible.
Yeah. I might be a little wrong, but something.
One final thing, and this is more me experimenting. I'm going to go and experiment with my sound field. And do you know Harpex? Spain and Natasha, they've written this thing that takes a first-order ambi sound field and using plane wave analysis, simulates third order under optimal conditions. I've managed to screw it up in many recording venues. It sits there going, I can't work it out. But I'm just wondering...
We were struggling to working out what would be actually optimal way to implement ambisonics when we were trying to publish the paper, so to make reviewers happy with, because there are all sorts of bells and whistles, and it's not trivial. So.
No, I'm going to go and piss around and have an experiment. Okay, thank you. You've given me some ideas.
Hi, just on a practical level, there are currently around 15 different versions of surround sound systems available for home and cinema, from the very early Dolby stuff to Oro and I can't remember what the other one's called now, Dolby Atmos. In my experience, both as a listener and somebody who does a certain amount of recording, none of them are ever reproduced properly. The results in cinemas are invariably awful. Most people's home systems, there are speakers put behind pieces of furniture. They're hidden anywhere that whoever is responsible for the decoration of the house. You're adding yet another possible system to this. How do you see it fitting into what is already, to me, an overcrowded and completely useless market? I mean, I'm a great fan of surround, it has to be said. I've been working with surround for 30-odd years now. But I don't find it realistic in any domestic circumstance, and usually badly done in any commercial circumstance.
Well, commercial, I mean, there are major differences now for something which is going to be a home environment and some large auditorium, because then there is extra time propagation between that loudspeakers add, and then there is also attenuation due to propagation. So that would need a little different treatment, I'm afraid. So it's not that we can take one thing and plug it into some small environment and a large environment. Because
I'm interested in how you plan, in how you see your system developing such that it can be used for both sorts of systems, or do you not have a plan for that at the moment?
Well, I would not discuss that now, but I'm thinking. Well, we would need to consider lots of things from scratch. I wasn't really thinking too much. I have some ideas, but I haven't thought in depth about how we would extend that to larger auditoria. But definitely, then we have all these time and level differences that come playing more important role. But I have to say, yes, I would agree with you. Somehow, it's never really satisfactory what you hear in home stereo, and yes, especially actually, it gets really annoying. After started doing this research previously, or perhaps back in the past, people were not having these home theaters and so on. But now, when I listen to something which is supposed to be home theater and loudspeakers are not placed properly, it just becomes really annoying. I'm thinking, like, can you make it mono, please? It's just this.
But it happens. I mean,
it's disturbing actually.
And the terrible thing that's currently happening with height systems is that people are sticking stuff in surrounds and in height because the speakers are there, not for any kind of logical reason. It seems to me that it's simply another effect. And I think for various people who want realism, which is what you're promising, it gets very
well. We're trying to commercialize this now, so we'll see how it goes. But there is much more to it. No, I mean, commercialization takes another different effort. But what I think is that we actually normally people. There were all these kinds of systems and people had good understanding, like, oh, you should take such and such microphone array, and then it's going to work well. But what we are bringing new here is to understand why that works well and why something else does not work well, and how to make it work optimally from this perspective for an arbitrary number of channels and so on, and what matters and what does not matter and how it matters and so on.
Yeah, very good.
Yeah, thank you.
Thank you very much. There's a company in Denmark called Intelligent Headset, which deals with a similar problem of 3D acoustics, but for headsets. And I've spoken to the company and said one of the biggest commercial fields they want to apply the technology to is conference calls. Because as everyone knows, having 6 people in Skype all overlaying their voices is barely unhearable. And one of the problems they've found is actually generating this 3D sound in real time, which is not possible with the technology they have right now. So my question would be here, is it possible to do it in real time? To do the calculations?
Yeah. I mean, if you're doing recording there and broadcasting, then yes, just transmission, yeah. I mean, it is possible even to create virtual space in real time owing to the scattering delay network. Or did I understand your question correctly? Or
Yes.
Yeah, and I mean, basically this is all just sort of recording and playing back. So we started with this idea of sort of broadcasting and recording and reproducing, but it turns out that there is much bigger market in gaming industry and so on, which is what we are not really doing in real time. But well, actually, some of it is done in real time if one wants to be interactive in virtual spaces, and that's where the scattering delay network, sort of a big challenge there is. Basically, what we want to do, if we want to create virtual environment, what we need to have is to have our microphone array and impulse responses of the source with respect to the microphone array in that given space. Now, calculating those impulse responses takes a long time, and that's not possible to do in real time properly. But that's why we have this approximation that we are not really calculating it exactly, we are just calculating what's perceptually most relevant, and it just works. Sensor would be able to say how much it takes in for implementation. Basically, when we have any kind of video game, most of the computational power is used to delivery of the video content, and very little then remains for audio. And we actually achieve this, just works like as a snap, basically negligible computational complexity. And there is basically no perceptual impairment compared to simulating all complete impulse responses here.
So this diagram that you got up here, you have not, it's not that you've calculated the first reflections and then fed them back into each other.
This diagram here, let me see. Well, sort of here is the first order reflection here, and there is, let me see. I would need to ask Answer about this.
What do you mean exactly fed back into themselves? I'm not sure.
Well, you see, we have sound source. The sound source, actually, these are first order reflections happening, hitting. The sound is hitting walls exactly where the scattering nodes are. And then they reflect back. And they not only reflect back to the microphone, but they reflect then to all other nodes. And they're just reflecting energy between each other. So everything that is coming then from to the microphone from this wall is actually coming from that same spot. But what is important is that basically what we hear is just the first order reflection. Then we have higher reflections, so the listener cannot really tell where they're coming, and there are more and more of those. And as the listener, sort of, as the source moves, the only thing that we need to recalculate is where exactly are first order reflections, and that allows for very, very quick adjustment of the whole thing.
Okay, so I understand now.
We have a demo with that, and you can see that it really works in real time. With some iPhone application, actually. So it is done in such a way that we are using detecting the location and your orientation, and basically you can hear a bongo there, and as you're turning, the bongo is staying exactly the same spot. And we're implementing this in iPhone because it takes basically no time to calculate it, and we are just using, and you can change the size of the room and reflectivity interactively and so on.
So those first calculations are critical.
Yeah.
The others are like you say, rough approximations, and they could be actually quite varied from that.
Yeah.
Okay.
So you see, this is what happens here. So this is what we are generating. First order reflection, and then second order reflection is, instead of going from here to exactly where would be on the wall, correctly, we are reflecting it to this node and from this node here.
And it's just, but
and we keep iterating like.
So it's not a feedback network. It's just a simple way of calculating more reflections.
Yeah, but sort of, if you look at precise mathematical diagram as a system. This is linear time invariant system, and there is a diagram which is exactly feedback delay network. So it is completely equivalent. Yes, there might be some sort of minor difference, but it turns out to be just a recursive system. So that is all there is. Nothing more in terms of computational complexity.
Thank you.
Perhaps one last question, because there's also a demo.
Hi, I'd like to follow on actually from two points made. The first one is about the commercial viability or applicability. And I was wondering if you had done any comparative analysis with commercial solutions. If I've understood what you've presented tonight...
Commercial solutions for what exactly?
Well, if we're talking about the creative industries, where we're not talking about capture with an eigenmic or something like that, but synthesizing an environment, what I've understood from this seems very like the old Q sound implementation of the Haas effect. And I was wondering if you had done any sort of analysis against those existing technologies.
Which exactly? So we are comparing to ambisonics, basically. That is what we did.
Okay, not Haas effect based things, which are...
What do you exactly mean by Haas effect?
Well, to me, it is principally just integral timing delay and level differences, and I think there's quite a substantial body of work that in the market as well as in...
No, if you would just remind me what exactly is Haas effect.
Oh, I would ask the professor for a clear explanation of that.
What exactly? There are many laws of the first...
The first reflection, arriving at the... defines the direction from which the sound came.
Time of first arrival.
Yes, sorry, first arrival.
Yeah. Well, basically, that would sort of make it. That is relevant to sort of being it immune to different kind of reproduction venues. I mean, if that is what you meant. So I'm not really sure that is pertinent to reproducing proper auditory perspective. Haas effect, from what I understand, I forget what's called what, but Haas effect comes into play sort of to this sort of working, not allowing too much interference with reflections in a room where we are reproducing it. If that is the law of the first arrival, that is what is place. Okay. It has not. Giving proper auditory perspective, it's a different thing, and we were comparing with competing technologies in that sense, which is intensity panning, and which is considered to be, from this sort of ad hoc methods, is considered to be most successful by many, and with ambisonics, which is systematic scientific framework, and we are showing improvements.
The second part is following on from the gentleman in the front row, really, because when you were discussing your room simulations for real time, the synthesis part is the part that I'm interested in, and I do subscribe to what I understand is called the precedence effect, that you neurologically disregard everything after the first reflection. But as far as I understand, what we're looking at here is purely azimuth. And we're not talking about perception of distance from the listener at all. And as you have this rather more exciting model than just a typical feedback reverberation, is that something that you've investigated at all?
Yeah, we haven't published results or haven't worked much on the distance, rendering the distance yet, but that's something, that we are working on, Yeah, rather that is. We had some kind of preliminary encouraging results and so on, but no really detailed studies yet to be publishable or presentable. And that is actually one direction that we are bringing it sort of further, rather than looking at larger cinema. I mean, large auditoria and making it 3D, etc. So there are many directions in which we can go in.
Thank you very much.
There aren't really many of us.
Can you make your slides available on the AES website?
Oh yeah, definitely. I'll be happy to.
Well, great. Probably we can head now to the demo facilities and hear the technology in practice. And thanks a lot, Zoran, for
thank you.
For the fascinating talk.